Hello! So in this video, I'm going to talk about something which is actually really important, but which a lot of people just kind of don't really point out because it's there. I mean, as you get more comfortable with using differentiation, you'll just use this, but you won't even necessarily realize that you're using it. So I'm going to point it out now. So first things first, I'm going to remind you of what a function actually is. So let's suppose I've got a function, f of x is equal to y, and let's suppose my function is x squared. So what is a function again? A function basically means that I take an x value, I stick it into my function, so I apply my function to it, okay, and then I get a y value out the other side. So I stick a value in, I get another value out. So for example, if my function was x squared plus 3, my function was x squared plus 3, then for example, I might like to put 2 in, okay, so I might put 2 in, okay, that means I square it, so it becomes 4, I then add 3 to it, so it becomes 7, so I get 7 out. Could do another value, so let's say for example, I put minus 3 in, okay, put minus 3 in, I square it, becomes 9, add 3 to it, it becomes 12, so I get 12 out. Put minus 3 in, and I get 12 out. And then I keep going like this, and then I can draw a nice graph of what's actually going on. Well, if you think, that's a bit like what we were doing in the last video, what we were pointing out in the last video. We put something in and we get another thing out. But with differentiation, we don't put a value in, we don't put a value like x in and get another value out. We put a function in and then we get another function out. So we get the derivative function out. That sounds a bit like a function, doesn't it? So for example, if we take our function, if we take x squared plus 3, we put x squared plus 3 into our, we're not going to call it a function for the moment, we're actually going to call it an operator. We're going to call it an operator. The reason why we call it something different is because with a function, we put a value in, we get a value out. But here, with differentiation, what I'm proposing is that we put a function in, and then we get a function out. So if we say that this is a function, then we're applying a function to a function. That can get really confusing. So I'm going to call it something different. I'm going to call it an operator. Okay, and my operator is my derivative, which I'm going to write like this, and I'm going to show you why in just a second. Let's suppose I put x squared plus 3 into my operator then. Okay, I differentiate it. So what's x squared plus 3 differentiated? X squared plus 3 differentiated. Well, the power comes down, so it's going to become 2x, and the 3 just disappears. It just becomes 0. Okay, so I get another function out. Right? Does that make sense? I put a function in, differentiate it, I get then another function out. Well, this is a really important idea because if you think about a number, for example, with a function I deal with numbers, right? So let's suppose I've got 3, okay, and that's equal to, well, I know that's equal to 6 over 2, for example, okay. Well, if I apply a function, okay, I can apply a function to both sides, and this is really important idea when I take things like logarithms. I can apply that, as long as I'm doing the same thing to both sides, okay, and preserve the equalityness of it, that's fine. So let's suppose, for example, I square both sides. So if I square this side, I'll also square this side. I'm applying the squared function to it, okay. Well, I can also do the same thing. I can also do the same thing with operators. So let's suppose I have y is equal to x squared, okay. Then I apply the operator to it. So my operator I'm proposing is d dx. Okay, so I'm applying d dx to this side, and then I'll also have to apply d dx of this side. This is the differential operator. Now, if I look at the left-hand side, for example, this d dx of y, okay, this looks a little bit like d dy by dx. If I think of this as a fraction, I know it's a little bit naughty to think of it as a fraction, but it actually behaves in roughly the same way. Differentiation it behaves in roughly the same way as a fraction. It's rise over 1, or change in y over change in x, okay? So, for example, dy by dx, for example, if I have 3/4 times 2, the 2 just jumps on the top. So that's a bit like what's happening here. I mean, it's not quite, but that's literally the same thing, okay? And then I've still got d dx of x squared. So actually, I don't even have to write down y. I can just simply write d dx of x squared and say, well, what I'm doing there is I'm applying my differential operator to x squared. I'm applying my differential operator to x squared. And if I apply my differential operator to my x squared, it behaves in exactly the same way. All that happens is the power climbs down and reduces by 1. So d dx, my differential operator applied to x squared, is just equal to 2x. Okay, so I started with y is equal to x squared. I applied my differential operator to x squared, and I just get 2x. It's just another way. Thing is, it's quite subtle. It's just another form of notation. It's just another way of writing down differentiation. But it's sometimes written like this, and it's not necessarily pointed out to you. It just suddenly gets introduced to you, and you just get used to using it, kind of almost subliminally. But I'm just pointing it out for you now, that essentially what's happening here, an operator is just essentially a function. You stick a function in, you differentiate, that's the operator, and you get another function out.